Hydraulic jacks and how they work. What is a hydraulic jack? A hydraulic jack is a type of hydraulic actuator. That means it utilizes the principles of hydrostatics to obtain a mechanical advantage from the application of a lighter force. How does a hydraulic jack work? There are 5 primary components of a hydraulic jack: the lever, the ram, the ball check valves, the piston, and the fulcrum. Before describing how each of these components work together, it is important to first discuss the fluid mechanical lenses we must use to dissect and understand the hydraulic jack. The basics of the hydraulic jack go back to hydrostatics and the hydrostatic equation. What all variations of the hydrostatics equation tell us is that the pressure gradient of a non-accelerating fluid in a gravitational fluid field is only dependent on the height of the fluid. This means that for a given contact surface at a certain height of the fluid, we can adjust the force applied simply by changing the area of contact. In the case of the hydraulic jack, the change in height across the working fluid is very small. This means that as a result, we can approximate the gauge pressure distribution along the working fluid to be uniform. The analysis of the hydraulic ram is most effective when we treat the system as being quasi-static. That is, the members of the system are moving so slow that although we have an unsteady boundary condition, we have a steady governing equation that is not time-dependent. As a result, we can connect each member of the system using free body diagrams and equations of equilibrium.
Now that we know that we must view the device as a quasi-static actuator with a working fluid of uniform pressure, we can begin our discussion of the device itself. When a downward force is applied to the second-class lever at a certain distance away from the fulcrum, there is a reaction force applied to the lever at the piston. We can write a sum of moments equation, concluding that the force felt by the lever and subsequently by the piston is as follows. The force applied to the lever multiplied by the overall length of the lever is equivalent to the force applied to the piston multiplied by the length of the fulcrum to where the lever connects to the piston. That same force felt by the piston must be equal in magnitude to the force exerted on the piston by the fluid. Thus, we can compute the static pressure experienced by the piston on the side that comes in contact with the fluid. Computing that pressure allows us to calculate the gauge pressure of the fluid, not only at the point of contact with the fluid, but also throughout the fluid, due to our assumption of uniform gauge pressure distribution. The pressure generated by the piston that is within the fluid is transferred into the ram. The ram's piston area is larger than the lever piston's area, which provides the ram with mechanical advantage. A sum of forces equation can be written to conclude the forces exerted on the ram is as follows. The hydraulic jack's performance is measured by how much it can amplify an input force, also known as its mechanical advantage. In total, the hydraulic jack benefits from 2 forms of mechanical advantage: multiplying the length ratio of the moment arms with the area ratio of the variable bore hydraulic cylinders generates the total mechanical advantage of the hydraulic jack.
The ram is unidirectional due to ball check valves. The ball check valves are 2 free-moving balls placed inside the pipes. When the lever is pushed down, oil in the lever area is pushed into the ram area through the open ram check valve. The movement of the ball check valves is determined by net force generated by pressure difference across the ball. The ram ball check valve is used to prevent the backflow of high-pressure oil stored under the ram from flowing back into the low-pressure oil inside the pipes, allowing for reciprocal lever action resulting in the buildup of pressure in the ram's piston cylinder. The reservoir ball check valve allows the lever area oil to be replenished from the low-pressure reservoir and prevents lever area oil from re-entering the reservoir when the lever is pushed down. The reservoir ball check valve opens and refills the reservoir when the ram is depressed in the reset process.
When exerting a force downward onto the ram, there is a resistance felt before the device is fully reset. During the reset process, the fluid inside of the ram is being forced downward and back into a small diameter pipe. When the viscous system moves downstream along a pipe, the Bernoulli constant decreases. Due to the drastic change in area when the fluid goes from the ram to the pipe, in order for the fluid to go from a large to a small area, energy is dissipated as the flow becomes separated. After the fluid moves into the pipe, the viscous dissipation factor of the fluid flow, which is a function of both the Reynolds number and the surface roughness of the pipe, comes into play. Essentially, the flow of the fluid downstream depends on the size, shape, cross-sectional area, and the diameter of the pipe. If the diameter of the pipe is small, then the viscous dissipation factor is large and vice versa. When the diameter is small, like in the case of the hydraulic jack, it's harder to push fluid through as opposed to a larger diameter pipe, which causes the resistance to be high.